Hello, this is Dr. Christy Patton-Lukes, a chemical engineering professor at Missouri S&T. This is a video for introductory transport phenomena based on Welty, Rohrer, and Foster's textbook, Fundamentals of Momentum, Heat, and Mass Transfer. We are going to do Chapter 3 in this video lesson. It's a really short chapter. It's only a couple of pages. But we're going to look at the fundamental physical laws, the fluid flow fields using both Lagrangian and Eulerian representations, steady and unsteady flows, streamlines, and systems and control volumes. Now, this is going to be a lot of definitions in this chapter. We're going to come back and use and apply these in the coming chapters. So let's start with an overall introduction. Basically, to understand fluid flow, we need 3 conservation laws and the mathematical descriptions of those laws. So we have conservation of mass, and we mathematically describe that using the continuity equation. Now, you may know this as a mass balance, but we're going to be reframing the vocabulary here. So the continuity equation is our conservation of mass description. Conservation of momentum is described by Newton's second law, and conservation of energy by the first law of thermodynamics. We are going to be working with each of these in the next few chapters, and we're going to get different forms of these based on how we choose to look at our system. Are we sitting still and watching things move around us? Are we going to float along with the movement? Are we going to look at the space, or are we going to track the fluid? Each one of these points of view gives a different understanding of the topic at hand. So first, let's talk about fluid flow fields. A field, you did these a little bit in math, okay? A field is a function of position and time in a region. When you did your differential equation course, you often look at a field as the solution to quickly get a feel for the solution and the direction things are going, okay? There are 2 basic approaches for analyzing fluid flow fields. We have the Lagrangian approach, where you watch one element as it moves through the field, and the location is going to vary with time. Time is the independent variable, not X, Y, and Z, time, okay? If you do the Eulerian approach, you look at the space, and you can choose any location. It's your choice, okay? The variables X, Y, Z, and T are all independent in the Eulerian approach. We are going to be adopting the Eulerian approach for this course. So X, Y, Z, and T can all be independent variables. Steady and unsteady flow. This one usually feels pretty comfortable for students, but point of view matters. So when I was writing the notes for this section, I was actually sitting on an airplane. I was sitting still. In my opinion, I was still. The earth was the one whizzing by, okay? So when we are talking about whether or not something is steady state or unsteady state, we need to know the point of view. As I'm sure you're aware, the easier problems to solve are going to be those that are at steady state or steady flow. In that case, the variables are going to have the same value at one particular location for all time, okay? But if you move to a different location, the value might change, but it will be that value, whatever it is, at all time. So the key is that time is not important in the analysis of steady flow problems, but location still will matter. So streamlines is the next term in this section. A streamline follows a line of constant velocity through the fluid flow field. If you took a tangent vector to the path from point to point, you would create a streamline. And it's a very handy way. So here in this picture, You see streamlines going over an airfoil. And then finally, we have the control volume. And you should have been introduced to this in your first chemi courses, but you know that we always need to begin a problem by identifying our system. What's inside the system, what's outside of the system. If the fluid is moving, this is a little trickier, right? So analysis of the control system, the material that is inside, is going to be a little bit more challenging once it moves outside of a device or a specific volume. Okay? So for fluid flow problems, it's usually easiest to keep an eye on the control volume. We look at a particular space and allow material to flow in and out, and we just watch the space. This will be the control volume approach. And when you see me using this, I will sometimes designate to remind you that that's what I'm doing by putting a CV. So CV for control volume. So this concludes our look at Chapter 3. In our next chapters, we're going to be developing the 3 basic conservation equations using the approaches introduced in this chapter. So thank you very much for your time.